Welcome to General Chemistry Mini Lecture Series, Lecture 46, Bond Polarity and Molecular Polarity. Bond polarity is related to electronegativity of the atoms bonded. As we already learned in previous lectures, electronegativity is the ability of an atom to attract electrons to itself. Fluorine has the highest electronegativity with an electronegativity value of 4.0, and electronegativity increases from left to right, from bottom to top. Noble gases are not assigned electronegativity values. Now let's get a little bit closer to bond polarity. The larger the difference in electronegativity, delta En, the more polar the bond. The negative end toward more electronegative atom. Therefore, the difference in electronegativity is used to determine the polarity of bonds. If the difference in electronegativity between bonded atoms is 0, equally shared, then the bond is pure covalent. If the delta En is 0.1 to 0.4, the bond is nonpolar covalent. However, if the delta Hen between bonded atoms is 0.5 to 1.9, the bond is classified as a polar covalent bond. If the difference in electronegativity is larger than or equal to 2, the bond is ionic. Right here, that's a pure covalent between delta En of 0.1 to 0.4, the bond is nonpolar covalent. But between delta En of 0.4 to 1.9, we call that bond polar covalent. If the electronegativity difference is 2 or higher, then the bond is ionic bond. And here shows the percent ionic character. Nonpolar covalent bonds have 4% or less of ionic characters. Polar covalent bonds have somewhere between 0.4 to close to 50% of ionic character. And if delta Hen is 2.0, then the percent of ionic character is 51. If the difference is 4.0, then that bond has 100% ionic character. Now let's take a look at bond polarity. Chlorine molecule, even though the electronegativity value for chlorine is pretty high, 3.0, but the difference in electronegativity is 0. Therefore, electrons, those two electrons, are equally shared by the two chlorine atoms. We call this bond, we call this Cl bond pure covalent. The shared electrons in hydrogen chloride molecule is, however, not equally shared. Those shared electrons, they are pulled much closer to the chlorine atom. The electronegativity difference is 0.9. That's within 0.5 to 1.9. That's why this HCl bond is polar covalent. If it's polar covalent, the molecule should have two different ends. One side is negative, partially negatively charged, and the other side is partially positively charged. We can also use this notation to show the partially positive end and the partially negative end. And here, that's an ionic compound. The difference in electronegativity is 2.1. Now we are going to take a look at dipole moments. Dipole moment is a quantitative way of describing the polarity of a bond. It can be calculated by the product of charge and the distance between two bonded atoms. The R is literally the bond length. The unit for dipole moment is dBs. Therefore, the dipole moment is directly proportional to the size of the partial charges, Q, also directly proportional to the distance between the two atoms, or the bond length. And the dipole moment is also directly related to delta En. Here shows a few examples. Chlorine molecule, delta En is 0, dipole moment is 0. No dipole moment. Chlorine fluoride, delta En equals 1, then the dipole moment is 0.88 dBs. When delta En is increased to 1.9, as in HF molecule, the dipole moment is also increased. That's the relationship between delta En and the dipole moment. Let's use the electronegativity values in this table to indicate the polarity of each bond. We have 3 bonds here. Let's take a look at the first one. The electronegativity trend for hydrogen and fluorine. Fluorine is more electronegative than hydrogen. Therefore, this HF bond has a polarity with a partially positive hydrogen end and a partially negative fluorine end. For CF bond, the carbon end carries partially positive and the fluorine end carries partially negative charge. Thus, the electronegativity for iodine is smaller than the electronegativity for chlorine. Therefore, the iodine end of the ICl bond carries partially positive and the chlorine end carries partially negative charge. The second example, we need to rank those following bonds in order of increasing polarity. Because all bonds, if you take a closer look, contain hydrogen, and hydrogen's electronegativity is smaller than all of the other bonded atoms, the trend in delta En should be the same as the electronegativity trend for the 4 other bonded atoms: nitrogen, oxygen, carbon, and fluorine. We use the electronegativity trend learned previously. The electronegativity for the 4 other atoms, fluorine has the highest electronegativity, followed by oxygen, the nitrogen, and carbon has the lowest electronegativity. So therefore, the trend in electronegativity difference for those 4 bonds should be CH bond has the smallest delta En value, while FH bond has the largest delta En value. Therefore, the bond polarity trend should be as the same as the electronegativity difference trend here. Now let's take a look at the polarity of molecules. When delta En between 2 atoms is greater than 0, then the bond between them has a certain degree of polarity. The larger the difference in electronegativity, the greater the polarity of the bond. So you can see here, carbon-nitrogen bond and carbon-oxygen bond. The bond dipole shows the nitrogen end carries partially negative charge. And for this CO bond, this is the direction of the dipole moment. Since the electron difference in CN bond is smaller than the electron difference in CO bond, the polarity of the CO bond should be greater than the polarity of the CN bond. That is because the greater the difference in electronegativity, the greater the polarity. If the molecular shape is symmetrical and all surrounding atoms are the same, then the molecule is nonpolar, regardless of the bond polarity. Let's take carbon dioxide as an example. You may say, oh yeah, the CO double bond, they are polar bonds. Therefore, this molecule should be polar. Yes and no. Yes, the CO double bonds are polar bonds. No, this molecule is nonpolar. Why? Because the dipole moment of the two double bonds here has the same amplitude but different directions. So therefore, the dipole moments of the two bonds, they are cancelled, and that leaves the molecule nonpolar. If the molecular shape is symmetrical and surrounding atoms are not the same and have different electronegativity values, the molecule is polar. For example, although this hydrogen cyanide molecule is linear, but the HCN molecule is still polar. Why? Unlike here, the dipole moments are cancelled. Here, there is a net dipole moment. The right end carries partially negative charge. If the molecular shape is asymmetrical, the molecule is polar regardless whether the surrounding atoms are same or not. For example, water has a band structure that is not symmetrical. The symmetrical structure are only the 5 fundamental geometries: linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. So bond is not one of those 5 fundamental geometries. So therefore, for this bond, the dipole moment is going that way. For that bond, the dipole moment goes that way. And there is a net dipole moment going this way, the negative end, toward this direction. Ammonia, each individual HN bond is polar. Since this is asymmetrical shape, there is a net dipole moment. IF4 ion, cation, while the dipole moment of those two bonds can be cancelled because they have the opposite direction, but the dipole moment of these two bonds cannot be cancelled. As a matter of fact, these two bonds dipole moment leads to a net dipole moment toward this way, with fluorine end carries partially negative charge. Similarly, in this ClF3 molecule, the dipole moments of those two bonds can be cancelled, but there's a net dipole moment right here. So therefore, this molecule is also polar. Those guidelines should help you in determining the molecular shape and molecular polarity. That's it for lecture 46. If this video is helpful, please subscribe to this channel and recommend those videos to other students who are also studying chemistry. I will see you guys in lecture 47, Introduction to Valence Bond Theory.